In this problem, we are going to look at the relationships between electrical power and mechanical power in a rotational system. We have an electric motor running on 10 volts and 54 amps. The diameter of the shaft is 3 centimeters, and the shaft is lifting a mass of 5 kilograms against gravity on Earth. And we're being asked, how fast is the mass rising in units of meters per second? So the fundamental assumption that we make for this problem is that electrical power is going to be equal to the mechanical power. This is not a bad assumption in many cases because electrical motors can be very, very efficient, as can the drivetrains. So on the electrical side, we have our equation for electrical power, which is just that voltage times the current is the electrical power. And we think about this with appropriate units. So in the metric system, we can say that watts are going to be equal to volts times amps. On the mechanical side, we might think of a shaft that's rotating and it has some torque and angular velocity. It also has a string or cord dangling from it with a mass and gravity acting on that mass. So mechanically speaking, we have the option to think of equilibrium, or not really equilibrium, but a balance of power between electric power and rotational power, or electric power and linear mechanical power. Let's first write out the equation for rotational power. So we have torque times omega, and we've seen this one previously. Now we could go about using this equation, and we were given a diameter or a radius of 1/2 centimeters, 1.5 centimeters for this shaft, but I think this problem is more easily solved by looking directly at the linear mechanical power. That's going to be force times velocity. Now, in reality, we have electric power is equal to rotational power is equal to linear mechanical power. And what the question is asking is how fast is the mass rising? So we can actually bypass this rotational power equation because what we want is a velocity for this mass as it's rising. So the velocity times the force mg, okay, is going to be equal to the mechanical power. And this, in appropriate units, can be thought of as newtons times meters per second, and that would then be equal to watts. So let me just go ahead and add that in here, okay, like this. Great. So now, if we balance the electrical power with the mechanical power, we can write it out as such. And we're solving for velocity. So the little v is equal to the big V times I, so voltage times current divided by the force. And we can do the appropriate substitution of parameters and write out this numerical expression, which ends up equaling 11 meters per second. Now notice we did not use the 3 centimeters for the diameter of the shaft, but we could have solved the problem using rotational power. So briefly, what we can think of here, if we wanted to do this with rotational power, and I don't have a whole lot of space, we can write that the VI is equal to TW instead. And W, okay, is then going to be equal to the VI over the torque. Now the torque, what is the torque? The torque is mg times this radius. Okay, so this would be VI over mgr. Okay, and the radius, this is a classic thing that I will continue to make as a mistake for the rest of my life, most likely, is that the radius is 1.5 centimeters. Okay, it's half of the diameter. Yeah, not very hard, but on exams and various other important things, I'll make that careless mistake. Okay, now, so we can figure out what the radians per second or the angular velocity might be for this rotating shaft, but that is not meters per second. So another equation that we'd have to use, we had to use r again essentially, and we do another equation of r omega is equal to V. Okay, and we talk, or the slides, I might not have gotten to the deep explanation this time during the introductory class, but it's based on the fact that if you think how much space or how much linear length you would map out with a rotation of a cylinder or circle, right, on the ground, right, that's going to be, of course, the circumference. And then you think about how that's being divided by the amount of time it takes, we can confidently write that R times omega is equal to V. Okay? So that would be another way to get the answer. It's just a couple more steps. And if you could be done here, but once again, if somehow thing happens and the parameters change, it's often useful to have some code written that you can just substitute in values, or used for substituting values. So let's go ahead and create code quickly, and we'll call this not a Google form, but a Google Colab file, where we have, we'll call it electric mechanical power. All right, and we'll do import numpy as MP, and we can go right either by pressing that button or, oh, I have too many sessions. Okay, I guess because we're doing the free Colab, let's go ahead and close these other ones. That's fine. We'll try it now. So let's see. Hopefully it will go ahead. Okay, fine. Manage sessions. Yeah, we can close these other ones like this. Okay, that's fine. All right, so let's now do it. And we'll create a new cell. And this cell, we're going to specify a voltage, so we'll call it big V. And that's going to be 10. And then the units, just to let us know, are volts. We have current, which is often given by I. That's going to be 54 amps. So like that. We have force, which we said is going to be equal to the mass times gravity. And I haven't specified those, but then I'm going to put in the units. This is going to be newtons. So let's go ahead and go back and we'll say M is equal to 5 kilograms. And we can put in G is equal to 9 point. You don't have to put that space, but I'm just do 9.8 meters. And I could do 9.81, I guess, like that. Okay. And my linear velocity, my little v, is going to be v times I divided by the force. And that, yes, will give us meters per second. And we're going to print this result. So v is equal to, oops, not that, print, or no, MP round v, and we can probably get away with 1 decimal point again, and we'll say this is in meters per second, just like this. And what do we get? We got 11 meters per second, which is what we calculated on the previous slide or in our numerical calculations by hand. All right. But again, if like, the problem says, oh, now the voltage is 5 volts. Now I just go up there and I type in 5 and it changes it. Okay. So it's very useful if the numbers that you're dealing with are going to be changing. Thank you.